Well, looks like we can get started. Welcome back, folks. Well, for today's class, we kind of have the announcements kind of just laid out for us here, but let's go through them anyway. We're on section 4.4, dealing with coordinate systems, and pretty much, well, there's two things we can say about this section. We're returning to that theme that we mentioned all the way back in section 1.1, that a lot of what you do in linear algebra is you just grab coefficients. The coordinates are going to be the coefficients that we're going to grab in this situation, but there's a little bit more going on in section 4.4. We're going to return to the concept of isomorphisms that we've been discussing, or really mostly hinting at ever since section 1.8 when we define linear transformations. And we're going to put that isomorphism to really good work. There's several problems in section 4.4 where if we tried to work with them directly without actually using the coordinate mapping, which is an isomorphism, those are really long, painful problems, and sometimes they require ad hoc methods to even complete. Finding issues with spanning linear dependence is not easy unless we're using the isomorphism that we're going to develop in this section. So that's going to be the major theme in section 4.4. And then 4.5, I mean, we could define this right now, but we're not in a great spot for that. We really want to do coordinate systems first. But finally, what we're going to do in section 4.5 is define once and for all what we mean by the dimension of a vector space. It's not as bad of a definition, except there's going to be some technical issues whenever we have an infinite dimensional vector space. But for just a preview of how all this works, let's put down a really quick problem. We can say, for example, that R2 has standard basis script E, and it looks like this. It's E1, comma E2. That's a lot of symbolism, so we can also write it this way if we prefer. It's a basis that goes 1, 0, 0, 1. So like we mentioned before, E1, E2 are just the columns of the identity matrix. So now this is definitely a basis. If we put those columns into a matrix, then there's a pivot in every row. That means it's going to span. There's a pivot in every column. That means those columns are independent. And those are the only two things we require for a basis, spanning and independence. But now looking at that basis, there's two elements inside there. Makes sense for dealing with R2. The dimension is the number of vectors in a basis. And so we get to say dimension of R2 is 2. Kind of a nice, clean little definition. Until we really look in section 4.5, there's a couple issues there. One thing we wonder is, well, there could be more than one basis potentially. Well, there really is. There's infinitely many different bases. And so we have to resolve, is every single basis for R2 always containing exactly 2 vectors? That's a yes, but R2 is a typical vector space. We have to wonder for any vector space V if that's true. So that's why section 4.5 does have a lot going on with it, even though the core definition doesn't look too bad to take on. So that's what we're going to be working through this week. And we have our upcoming third exam. One thing I try to do when I write out these exams is I usually don't like to put material that would involve this week. Oh, let me see if I can select that. This week right here. Well, this week, April 8th to 14th, I don't think I can select it to highlight it. The reason for that is any problems I assign on this week, I don't have the opportunity to grade and get back to you. So probably what I'm thinking about for exam 3 is the coverage is going to go from where we left off on exam 2 up to section 4.5. So this is going to be the last one that's actually on exam 3. But over the weekend, before we come back to class on Tuesday next week, I'll have the exact coverage posted here so we know exactly what sections and the sample problems that we are expecting as well. Well, any questions at all, folks, with any of those announcements? Okay, well, let's now take a look at just what's happening in section 4.4. And just for a preview of what we're getting into, let's take a look at section 1.8, 1.9, and preview the big punchline of section 4.4. In section 1.8, the major thing that we mentioned here is, for a lot of folks, you could say linear algebra is all about studying these linear transformations between vector spaces. That was a mysterious word in section 1.8, but thanks to chapter 4, we've all been slightly traumatized and we know a little bit better what's meant by vector spaces. Then we expanded on this and we discussed that if you have a linear transformation, well, it satisfies this property. It preserves the operation of vector addition in the domain and in the codomain. It's also operation preserving because it preserves scalar multiplication in the domain and over here in the codomain, which would be W. So that's what linearity is required to do, be operation preserving. But if your transformation is also one-to-one and happens to be onto, we call it something special. It's called sometimes an isomorphism, if we want to be more explicit, a vector space isomorphism. And what this does for us is essentially what this is doing right here when we read through it the first time. The concept of counting in German looks like something totally new, but it's not. We're just using different terminology to express the exact same concepts. That's what an isomorphism is going to do for us. We'll take something that looks really complicated, say a problem like this one, determining if P1 and P2 are linearly independent. That's a complicated problem, and you can imagine it gets worse with more vectors. But it turns out P2 is isomorphic to R3. If we really wanted to, we could just take these two polynomials, apply the isomorphism, and do all of our work back in R3. In other words, no matter how nasty this looks, we can turn it into a chapter 1 problem. And that's why I keep mentioning chapter 1 is probably the more pivotal chapter in the entire book. It's a good one to return to and read through again, even if you're just skimming as you read, because a lot of concepts in chapter 1, you really didn't have the feel for where they were going until we're at this part of the course. So in section 4.4, that's what we're going for, a coordinate mapping between some vector space V. Typically, that space is something hard to work with, like a polynomial space or a function space. But if we map it into Rn, whether that's R2, R3, R12, who knows, then every single concept that we've studied in chapter 1 over here will apply to your more esoteric vector space, whatever it happens to be. So that's literally what we're going to be working on today. We're going to use the coordinate mapping to show that this set of polynomials forms a basis. And it's really hard to appreciate just how much work that is. So for the brave, try doing this problem example 5 part A again, but using only the methods that we did right here in example 1. This is pages and pages of work, but it could be a fun algebra adventure if you're a little bit bored one day. So that's what we're going on in these sections. And now let's start at the very beginning. First, any questions, folks, with that introduction to 4.4? Okay, well, now going through this, one thing that I should think about is, because this is a fully Zoom class, well, maybe not. I was going to say I could turn the monitor back to at least a 1080p display, but I would have to fix that for my next class. Let's keep it the way it is right here. So I have a bunch of definitions that came from the prior chapters of the book, just to connect the thoughts. And this is where the new content begins, right here. So first, we have the definition of a basis. And just as a good reminder, a basis for a subspace H of a vector space V is just a set of vectors in V, which would also be in H, that happen to be linearly independent and also span the space H at the same exact time. So once we have that, here's some dots we can connect. Linear independence tells us that if you go to solve this equation right here, well, you'd probably augment this into a matrix and you would find there's no free variables. The columns are independent. If there was a free variable, those columns would be dependent. And that's why we get to say uniqueness right here comes from linear independence. There's a unique set of scalars, C1 through Cn, for which x equals that linear combination. And those scalars right there are what we're referring to as the coordinates. So that's the purpose of linear independence. Next, the fact that there even exists a solution is due to spanning right here. Spanning means that this equation right here must be consistent. There would be a pivot in every row, but there could not be a pivot in the far right column any longer. And so we automatically have consistency. And that's why those scalars exist in the first place, these scalars right here. So essentially, theorem number 7, it's got a really fancy name, but this is the one time where that fancy name is not something that's going to come back to haunt us. It's not a theorem that we necessarily try to apply all the time. The purpose of that theorem is to make this definition happen. And when you really read this theorem, it's just basically a retooling of the definition. Again, existence is spanning, uniqueness is independence. So that's the unique representation theorem. It tells us if you have a basis like this, of vectors b1 through bn, then you could always form the linear combination involving those vectors. You can come up with scalars c1 through cn, and those scalars will be unique. Because of that uniqueness, the next definition tells us if we grab a basis, then the coordinates of x relative to that basis, or the b coordinates of x, I'll usually say the coordinates of x relative to the basis, are just the weights, or you could call them scalars, such that, once again, x equals that linear combination. Because of the importance of these things, we have brand new terminology. Instead of saying the coordinate of x relative to the basis b, we'll write this instead. So this is a huge paraphrase of that statement. It's clunky looking terminology too, or notation rather. We put x around with a bracket. That helps us remind us that we're putting down a column vector right here. We also put in as a subscript, let's zoom in on that, the script b, to remind us we're operating on that basis right there. So in other words, with this new definition, all we're doing when we say grab the coordinates for the vector x relative to a basis, we're just solving that linear combination and writing it in as a vector like that. That's going to be our coordinate vector. So that's our brand new definition. This definition turns into a mapping, which is going to be linear, one-to-one and onto. So we're essentially looking at an isomorphism right here when we work with this. And that's what we're going to define down in the notes later on. But any questions or comments so far, folks? Okay, so I would say this, coming down to this, is so far the big takeaway. There's just a lot of vocabulary, a lot of different notation being applied here. But if you remember this big takeaway that all that matters is the coefficients, we throw them in there, just like we did in section 1.1, then you're on the right track. So here's the transformation. If you take some vector space V from the domain, that's what's going on right up here, map it to Rn, that makes sense. There are n vectors right, or excuse me, n entries right here. So that is a vector inside Rn. Then we'll call that mapping the coordinate mapping determined by the basis B. We'll come back to that transformation there when we're about in the middle of the notes. But for the moment, we're going to practice with this right here, where the purple notations are, just to get a feel for how all this works. So here's the setup in example 1. I have 3 different vectors, v1 through v3, and then a bold claim is made. It says, then this is a basis for R3. When you see that written down, especially if you're in an exam setting, definitely take it for granted. You don't have to verify it. You don't need to do a determinant or anything like that. Just trust me, it's definitely a basis. If it's something else like a lecture problem and you're curious, we can double check it. But for the sake of an exam, definitely that's a comment I want to get out there. Any statement like this, you don't have to double check. What we'll do is find the vector x such that its b coordinate vector is this right here. This turns out to be the faster problem, and let's show exactly how it goes. The moment they gave us the coordinates of that vector x relative to that basis, we have a linear combination that looks about like that. So let's start by writing out this type of linear combination. We'll say that x equals You can use C1 through Cn, but I typically use X1. Then instead of B1, we're using V1 right here. Those are our vectors. Let me try to fix that. There we go. So there it is. That's our linear combination. And now what we have is a vector equation right here. Once we solve this vector equation, we'll find out what, oh, excuse me, I'm getting a little bit backwards on this. We essentially have this already solved. We just need to put in the right values. We wrote down this linear combination here, much like this one. But once they gave us the scalar values, that's the step I got mixed up on. We just take these and plug them here, here, and here. So this one is just a really fast problem where we go x equals 0 times v1. v1 is 1, 0, negative 3. Plus x2 is a negative 3, so I'll go minus 3 times v2, and v2 is the vector 0, 2, 1. Then x3 is a 2, so we'll go plus 2. Negative 5, 1, 2. So there are those coefficients once again. And now we just need to perform the linear combination and find out what x equals. Any questions at all so far, folks? Okay, one thing I'm noticing that since this is a Zoom-only class today, I usually look over here after I ask you all for questions because that's where I see all the chats and stuff like that going on. Probably looks like I'm ignoring you because I'm not looking directly at the camera where you all are. Sorry for that. That's kind of weird. We'll just get through it together. So let's keep on going on this thing. The linear combination is pretty fast. We're going to get from right here, this is 0, negative 6, negative 3, plus from this location, negative 10, 2, and 4. Then let's just add those up. And the vector x is negative 10, negative 4, positive 1. Well, we did it, folks. If we have the coordinates relative to the basis b of x, finding the value of x is just a matter of writing down the linear combination, plugging in the coordinates, and just evaluating the scalar multiplications and vector additions. Any questions with those steps there? Okay, so this is again the nicer problem where we just crank out a linear combination. We did that in section 1.3. That's like week 2. Only difference is we have a whole bunch of different notation this time. But this problem right here is the tougher problem. We have a different basis. So v1, v2, v3 are indicated here. They form a basis, and sometimes it's good to be specific. Let's add here just to say is a basis for R3, which makes sense. There's 3 vectors in R3. Now we want to determine the coordinate vector of x relative to that basis up here when x equals 3, negative 5, 4. Example 2 is the reversal of example 1. We still do this first step of forming a linear combination, but this time that's unknown. It's our job to find it because there's no values given for this right here. So to start off the problem, let's indicate what we want to solve. We want to find the coordinate vector of x relative to the basis b, and it's going to look like this: x1, x2, x3. If we can solve for those, our job is done. Then we reverse engineer the definition and say, well, if this equation holds, then that means we can take x1 times v1 plus x2 times v2 plus x3 times v3 and set it equal to the thing that's known, this x right here. That one's special. Let's give it a color. Okay, so that was the weird thing I got conflated with on this one. On the prior problem, example 1, we knew the coordinates, and so it was a fast problem. Here, the coordinates x1, x2, x3 are unknown, so this one turns into a row reduction problem. It's a little bit longer, but it's really chapter 1 type techniques we have to use. So the first thing we'll do is take this vector equation. You could write it as a matrix equation, as a system of equations, but at the end of the day, what we really want is the augmented matrix. For that vector equation, it will go start with columns v1, v2, v3, and we drop the coefficients x1 through x3. So it's going to be 1, 0, 3, 2, 1, 8, 1, negative 1, 2, augmented with 3, negative 5, 4. And what we're solving for in this augmented matrix is the unknowns highlighted in yellow. So this would be essentially the first step right here in solving any problem like this one, the longer version. But now that's row reduction, a good reminder for this process is this is the longer row reduction. We need reduced row echelon 4. In other words, this part right here is automatically going to be row equivalent to I3, the 3x3 identity matrix. We'll have a pivot in every column, and that's an automatic guarantee because we said those columns form a basis. There has to now be a pivot column in every single column here. And so there's a lot of row reduction we sometimes have to do. But it's good to know what we're expecting. If we don't get the 3x3 identity matrix, then we've probably made a mistake in row reduction, or maybe I screwed up and that's not really a basis. But I double checked it this morning. It really is one. So let's start row reducing and see what we end up on. Looks like we just have to clear this 3 for a first start. So I'll copy and column rows 1 and 2. 1, 2, 1, 3, and 0, 1, negative 1, negative 5. Now multiply row 1 by negative 3, add to the third row, and we get 0, negative 6 plus 8, so a 2, negative 3 plus 2, so a negative 1, negative 9 plus 4, so a negative 5. And that finishes out our first step. Let me know if any of my numbers go sideways. That's the easiest thing to mess up in linear algebra, some of the arithmetic. There's so much of it. On the next step, I'm going to copy in row 2, eliminate entries above and below. So now we have row equivalent, 0, 1, negative 1, negative 5. Let's start with this 2 right here. First column 1 cannot change, so I'll go 1, 0 just to fill it in. Then multiply row 2 by negative 2, add to row 1, and we should get 0. This will be a 2 plus 1 for a 3. This will be a 10 plus 3 for a 13. And now same operation, multiply, well, sort of the same operation. Multiply row 2 by negative 2, but this time add it to row 3. And we get 0. That was negative 2, so this turns into positive 2 minus 1, so we get a 1. This will be a 10 minus 5 for a positive 5. So everything is settling up. We have the first 2 columns of the identity matrix, so that's a good, nice little check midway through the problem. Only thing we need to do now is clear off those 2 entries. So let's do those standard row operations. This is now row equivalent to 2. Next line, 0, 0, 1, 5. I'm sensing we're probably done at this step, so let's put in the augmented as a reminder, the augmented symbols. Now columns 1 and 2 can't change, so let's put in 1, 0, 0, 1. And for our first operation, take row 3, add it to row 2. We're going to get 0, 0. It's kind of nice. Next operation, negative 3 times row 3, add to row 1, is going to give us a 0. Let's double check. Negative 15 plus a 13, so a negative 2. And now we've got the 3x3 identity matrix. We just need to say, what is the solution? Well, we are solving an equation involving x1, x2, x3. So you might write, this implies x1 is negative 2, x2 equals 0, and x3 equals 5. But what I would encourage you to write on your paper as an overall conclusion would be this. you want to say, therefore, the notation and terminology is tricky. So the more you write this, the better the connection you have with the new material in this section. So definitely write this out in your work. The coordinate vector of x relative to the basis b is -2, 0, 5. And we did it. We determined the coordinate vector x relative to the basis b. It's this right here now. Well, that's definitely a process, but observe a lot of what we're doing in chapter 4 after we got past section 4.1 is really just looking at chapter 1 with a new lens, adding more terminology and processes. This is a problem we could have done in chapter 1, but we've had to talk about a lot of weird stuff like bases, for example. Well, any last questions, folks, on the conclusion here? Okay, so with the coordinate mapping, it being an isomorphism, it has lots of importance. But the trouble with the coordinate mapping is it depends on a basis. These bases are weird. They're not nice to work with. Sometimes what we like to deal with is the standard basis. So let's take a look next. I think this is the next problem for what standard bases could be. Now, this is a good reminder that I try not to put too much fluff into these notes. Most of the questions that you see here are definitely standard good concept type questions. Some of them have lots of computation, like this one. I try to limit those on real exams because I don't want it to be more than 75 minutes. Other times they're really fast, like this one right here. But the exam is about telling the difference, knowing when you have a fast process or when you have something that does require extra computation. But sometimes an exam question is just purely a concept question, like this one right here. Write down the standard basis for R2. We've written this down before, but let's write it down again just as a reminder. For bases, we like to write this out, a cursive B. But a standard basis is different. When you see that, we're talking about a basis that's just canonically there for R2. And we go to the next symbol, E. Just fine to write it this way, but for this set, it's usually written as a cursive E, something like this. The standard basis goes E1, E2, and if that's all you wrote down on exam 3, that's good enough for me. I'll assume you know what E1, E2 is, but let's put it down here for emphasis, at least for the notes. Where E1 is 1, 0, and E2 is 0, 1. It's a terrific basis, and this basis right here, again, is called the standard ordered basis. Now let's do the same for P2. Writing down a basis for P2 is kind of tricky. First thing you'd want to do is think about what is P2. Let's just write it down this way. P2, it's a set. I won't use set builder notation. I'll just use the curly braces to emphasize it's a set. It's the set of all polynomials let me try to spell that right, polynomials, there we go, with degree at most 2, according to that subscript right there. So if it has degree at most 2, then we can write the standard basis this way. Still, we like to use the symbol E if we're dealing with the standard basis, even if it's for a non-standard vector space like P2. But if we ever have a conflict of notation between this one and this one, you can just add an extra symbol to it, like say a prime symbol. I'm not saying we're differentiating it, we're just telling them apart from this one to this one. Some people like the hat symbol, so you could go this way as well. I'll go with the prime symbol. It looks a little bit less offensive, I guess you could say. So this standard basis, well, to get all polynomials with degree at most 2, you first need the constant polynomials. So you need a constant function, and that's about the easiest constant function ever, the function that always evaluates to a 1. Now, our author writes down these functions in this way, but some people would potentially write them in this way. just naming the function, that's kind of clunky because then you have to say P1 equals, let me restart on this one. P1 at T evaluates to 1 for all T and R. And so that gets really pretty clunky. You'd have to define all three of the functions. So our authors use a notation right here of just putting in a number, but regarding it as an actual constant function is a pretty standard way to go. Mainly writing down this because the standard doesn't help us. This is also kind of confusing to know they meant a function. So that takes care of all the constant functions. Next is the linear functions. And if you put this in and do any combination of 1 times a variable, or excuse me, 1 times a scalar and t times a scalar, now you have all the linear functions, and then go off to t squared. Now you can build up any quadratic, and we stop right here because the degree was at most 2. So that's how we would typically write down a standard basis for P2. If we did it for P3, looks about the same. You just add a comma and go up to T cubed. Well, any questions, folks, with those standard bases? Okay, so what we're going to do next on example 4, it's a really short example, but it's kind of a preview to where we're going next. It says find the coordinate vector P relative to the standard basis of P2. So what I would encourage you to write as part of your answer is, from this portion right here, your answer should be indicated this way. So I put brackets around P to say we're doing the coordinate vector. The brackets are a reminder that we're mapping into R3, yes, R3 this time. We also put down this to say, which basis are you using? We're using that one, E prime. And then all we have to now do is pull coefficients for the linear combination that builds P of T relative to this basis. But that's why we call this one the standard basis. The work is pretty much immediate. For example, even if we did this very, very precisely, let's actually do it and show how it works. You might say, why didn't you just grab 1, 3, and 4? That's the theme in linear algebra. That's how it should all go. Let's explain why it works that way. Why 1, 3, 4 should go in this location. So first, to get the 1 right here, you have to take a constant and multiply it by the first basis vector, which is that function right there, the constant function, which is 1. Then next you would go plus. To get 3t, well, we need to rescale 3. So you need to take a constant 3, multiply it by this basis vector, t, and then rinse and repeat. To get 4t squared, you need to rescale this one by 4, so plus 4, multiply by t squared. And we really didn't do a whole lot. It looks like we just rewrote the function, maybe added some color coding, one multiplication symbol. But the punchline is, because we used these, the actual basis vectors went inside to form this linear combination. It means we have the coordinate vector. It is a 1, 3, and a 4. So in other words, if you ever have to find the coordinate vector and you're using the standard basis of P2, you're just pulling coefficients, just like we did on the first day of class to solve our first linear system. Well, that's a pretty fast problem. We made a kind of a mountain out of it by doing this, but it's good to see the process. Any questions at all, folks, on getting that vector? Okay, so essentially what we've done is we've taken P2. P2 is a complicated space of vectors, all polynomials with degree on most 2, and we decided, well, we can work right here in R3. And because these spaces are isomorphic, every single concept back there in R3 from chapter 1 will apply over here to P2. That's the amazing power of linear algebra and those linear transformations. And so that's what we're going to be getting into really shortly. So first, here's, again, another wall of text. The thing that's new in this section, it starts right here. And everything else above is just connecting the dots. We have the reminder of what it means for t to be linear, the operation preserving parts 1 and 2. But then when we were in section 1.9, we spent some work on dealing with when is t 1 to 1? That's if it's standard matrix, if we can find a standard matrix, has a pivot in every single column. On 2 would have a pivot in every single row of its standard matrix. If it's also linear, now we have an honest vector space isomorphism. And so that tells us, no matter how different W and V look like as vector spaces, and I assure you some vector spaces are pretty wild to look at, when we think about the operations of vector addition, scalar multiplication, if you can find that isomorphism, it tells us, because linearity is operation preserving, as far as vector spaces go, there is no difference between V and W. Typically, we think of W as being the simplified space, like R4, and V as being the complicated space, like, say, P3. So this is, again, what we were hinting at the start of class, really the whole semester. If we have a basis, B1 through Bn, of a vector space V, then we can define a coordinate mapping from V to Rn just by doing this. Take your vector x. That vector x comes from V. Again, that could be a really complicated, convoluted looking vector space, functions and things like that. But you map it to this thing, and this is in Rn, where we've been studying that extensively in chapter 1. And the work in Rn is always greatly simplified if we have something complicated inside V. So this is the major reason why we suddenly care about coordinates. What basis does for us is allows us to pull coordinates. And if we can map in this way, we have an honest vector space isomorphism. V and Rn are essentially no different. The only difference is notation. With all that said, and we did say a lot, we're going to apply that right now and show that this forms a basis for P2. Again, this is a pretty complicated problem if we skipped the fact that we have an honest isomorphism. Doing this in P2 is hard, but doing it in R3, no problem at all. We can make this a pretty fast problem. Any questions at all, folks, with that theorem 8 before we get started? Okay, to help us along, let's also take a look at back into the Moodle website. We have our invertible matrix theorem. I'm kind of just moving it down as we go from week to week, because I assume if you're about to do an assignment, you probably want to look right there. The invertible matrix theorem, it's going to help us out in a lot of ways. Let's take a look at the question. It says, show that that set of vectors forms a basis. So now we can go back to the invertible matrix theorem and notice, let's see here, the columns of A forming the basis is on this set of statements that are logically equivalent. So I'm going to tie this together with maybe this one. Let's do a determinant. It's been a while, so that's a good refresher. You might do a whole different strategy, and that's completely fine. You might row reduce your matrix and show that it has the right number of pivots, and that would qualify. But I'll try to attack it through this right here. So joining parts R and M together. But that's hard because I can't just throw those into an actual matrix A. These are not matrices, they're actual polynomials. So the first thing we do is this. We're going to map the entire problem into R3. We do that by setting A equal to this. First, let's also put in some terminology or some notation so we can see just what we're doing. Let's call this function right here P1. This function will be polynomial 2, so P2. And this one with the 3 terms will be P3. So now that we have that down, we want to take the function P1 and pull coordinates relative to the standard basis. I'll call it just script E since we don't have 2 of them on the same page we're looking at. So that's going to be column 1. Column 2, take P2 and map it to its coordinates relative to the standard basis. Rinse and repeat. P3 maps to that coordinate vector. And for completeness, we ought to say what E is. It is 1t, t squared. Again, we stopped at the 2 right here because we're building polynomials of degree at most 2, indicated by the p2. If that said p5, we would have kept on going until we got to t power 5 to get 6 vectors in total. So that's our standard basis E. Then coming back over here, all we do is take this polynomial, repeating the same problem that we did over here, just pull the coefficients and you're building the right column vector. So it just feels like section 1.1 all over again. The massive theme in linear algebra is all we care about is coefficients. So when we see a 1 plus t squared, any volunteers for what coefficients should go in?
One and one.
Good call. This is going to be 1 and 1. So it should go, oh, didn't mean to scribble on it. Let me fix this again. We have a 1 coming from the constant term here. There's no term involving t, so we do throw a 0 in. But then the coefficient for t squared is a 1, so we go 1, 0, 1. So that's our first step. Next, we're mapping this way. Any volunteers for the next step?
Zero, one, one.
Exactly. We're missing the constant term on that one. So we put in a 0 to wipe out that, just as you said. So 0, 1, 1. And that's pretty much the name of the game. I'll do this one. It's 1, 2t, t squared. So we would put in 1, 2, 1. Well, we did it, folks. We have mapped into R3 now. So now we're dealing with these column vectors inside R3. If those column vectors form a basis, then the original set of vectors is also a basis, since every concept that happens now over here in R3 with these columns are equivalent concepts back into the domain space, P2, before we did the coordinate mapping. So again, that's why isomorphisms are really powerful tools. This is a very computationally intensive process if we're doing it by hand, but we've built up so much theory with linear algebra in R3 or Rn in general that this is not so bad. Let's hit it with the determinant as promised. We can say determinant of A equals, we don't have a great number of zeros, so instead of just hitting it with the cofactor expansion, I'm going to try and eliminate that entry there. First, we have to use equality because we're not using row operations in a certain sense. And the first step isn't a row operation. We just get a 1, 0, 1, 0, 1, 2, 1, 1, 1. On my next step, I want to eliminate that one. And it feels natural to write that squiggly tilde line for row equivalence. But because we put a determinant symbol on there, this whole thing right here is a number. And for numbers, we use equality instead. Kind of jarring. So inside right here, let's copy in rows 1 and 2, 1, 0, 1, 0, 1, 2. We'll multiply row 1 by -1, add to the row below to get 0, 1, 0. Next, let's do a cofactor expansion going down this way. We take the scalar 1 here, multiply it by a reduced determinant where we eliminate this row, this column, carry in 1, 2, 1, 0. If anyone took the row reduction process, you might have beaten me, but still good review on doing determinants right here. Because the rest of the entries are 0, this is the entire column 1 cofactor expansion. And now times 1 falls away. Main diagonal product is 1 by 0, minus off diagonal is 1 times 2. So the whole thing equals -2. And let's double check the theorem. Because this is non-zero, determinant is non-zero, we have that the columns of A form a basis for Rn. Let's say that next. Since determinant A is non-zero, its columns forms a basis for R3. But that's not the full story. It's not even the conclusion we want. The conclusion we want is relative to this set forming a basis for P2. But what happened with that matrix A was we got to there from the coordinate mapping of those polynomials. So this is our big conclusion we really wanted. We can now say, therefore, B, this set, 1 plus t squared, t plus t squared, 1 plus 2t plus t squared is also a basis for P2. Deserves an exclamation mark because that is a pretty weird way to calculate. And it's a massive shortcut as well. Any questions at all, folks, with the conclusion here? Okay, actually, let me try to do this differently. I'm going to take this along with us so that we know which basis we're working with the follow-up questions. So now that we do know it's a basis, this question makes sense. You can ask about what is the coordinates of some polynomial Q relative to a basis B, because we just proved it's a real basis. So this says we have coordinates for some polynomial function Q, and we want to say determine Q of t. In other words, what is the polynomial Q? To do that, we still have to use this basis from before. Let's put it down there, kind of out of the way. And this is like example 1, our first problem of the day. This is the easier route to go because the coordinates right here are already known. So we get to say that Q of t is another polynomial function, and it's formed by taking 1. Now, watch out for the symbols here. Again, all these things are important. When it says the basis b, that means the scalar 1 is going to multiply that function, which we call p1. So 1 times p1 of t plus, oh, that's a -2. Let me try again. Minus 2 times this polynomial, p2. But because we're doing a function or a valuation here to determine this, we'll write it as p2 of t. Then finally, plus 0. I put the 0 in on this one just so it's a slightly faster problem. I probably would do that on a real exam question as well. 0 times this polynomial, the p3. So p3 of t. So it's a pretty fast process. All we're now doing is some substitutions. It's 1 times p1, so throw in p1 to get 1 plus t squared. Then we have -2 multiplying p2 of t, so we go down to p2, it's t plus t squared. I think we're done with that basis, but let's park it down here just in case. All we have left to do is just, well, a little bit of algebra. This is the relaxing part. We can distribute the -2 through to get 1 plus t squared minus 2t minus 2t squared. Combine our like terms and we get 1 minus 2t minus t squared. Well, we did, folks. That's the coordinate, if that's the coordinate vector of q, then the original polynomial q must have been this right here. Any questions at all, folks, on that conclusion? Okay, well, now that we've seen how that process goes, we need to turn it around and see what would happen if we know the actual polynomial, but we want to find the coordinate vector P relative to the basis B. Well, we'll still do the same thing. I shouldn't have totally deleted that. Let me just put it right here. As a quick reminder, here's that basis B again. And this problem right here, let's say just to convey what we did earlier in the notes, this is similar to example 1. And this one is similar to example 2. It's definitely tricky, so here's what we're going to do. Let's come down here and write out, it says, find the coordinate vector P relative to the basis B. And a good strategy with a technical question like that is write down what you're going for. It's going to help our subconscious kind of connect the dots and that kind of stuff. And it just gets us started thinking about the problem. All of this is saying, find the coordinate vector of P relative to this basis B, which would be written out in this way: x1, x2, x3. If we can find those coefficients, we're completely done. So now to get those coefficients, we have to go back to this basis B. Let's recall that this is P1, P2, and P3. And we just write down the linear combination. We take x1 times P1, but if you did that, you're now working fully in the polynomial space, and that's pretty difficult. Instead, let's abuse that isomorphism again and put in the coordinate mapping of P1 relative to the basis E, the standard basis. Let's put it down here since we're using it just as a quick reference. 1t and t squared. Oh, and I just saw a chat. Christian asks, oh, no worries, Christian. This should be uploaded before my 7 o'clock class starts. Take care. So next, we'll map this one back into R3, where all of our work is a lot easier to get through. Then go plus x2. We're not going to work with that one directly either. We're going to map it. So P2 coordinates relative to the basis E, the standard ordered basis. Then down the line, x3 multiplying P3 relative to its standard basis will be equal to, well, now this is a vector equation in R3, so my right-hand side is not going to be P of t either. It's going to be the mapping of that polynomial, the original one, with respect to the original basis E, once again. So that's our setup right there. And again, this is pretty much example 2. We have a big old vector equation. And what we immediately do next is form the augmented matrix for this vector equation. So we're about ready for the next step, folks. Any questions at all with the earlier organization? Okay, well, let's give this a try. The row reduction steps on this one aren't going to be too bad, but keep in mind, because these vectors really did form a basis, we've mapped them to a different basis. When we row reduce, it's just like example 2. We want reduced row echelon form, and we should see the identity matrix to the left before the augmented part on the right. So here's how it all goes together. First, well, we're remapping P1 relative to the standard basis E, and we're just copying that work for part A of this problem. We get 1, 0, 1. The next vector, it's going to be 0, 1, 1. For the next vector, we have 1, 2, 1. Then augmented with this vector right here, which came from this polynomial. And so its coefficients should go 1, 0, negative 1. So that's our augmented matrix. And it doesn't look like too much row operations we have to take care of. What we'll be solving for are the unknowns in the vector equation, x1, x2, x3. So first step, let's copy in rows 1 and 2 and eliminate that 1 down there in row 3. We have that this is row equivalent to 1, 0, 1, 1, then 0, 1, 2, 0. Finally, multiply row 1 by -1, add it to row 3, and we will get 0, 1, 0, -2. So on this step, we've got column 1 all resolved. In column 2, we have a bonus. There's a 0 above. We just need to remove the quantity down below and make that a 0. So we can copy in rows 1 and 2 once again. 1, 0, 1, 1. 0, 1, 2, 0. Now the operation starts. I'll put the 0 here since that has no possibility of changing. We'll multiply row 2 by -1, add to row 3 to get 0, -2, -2. Here's where you could take a big shortcut. If you erase this and put in a 1, 1, I think that's a good time-saving step. That always looks really confusing on the notes, so I always take this additional step, but you don't have to. If you see a natural shortcut to take in your row reduction, you're going to notice a lot of patterns, especially at this point in the course. I'd say take it. You would always be welcome to do so. So I'm going to change row 3 by just dividing by -2. It's now 0, 0, 1, 1. I'll copy in rows 1 and 2 just as they are. So row 2 is 0, 1, 2, 0, 1, 0, 1, 1. And now we are finally there. We need to eliminate those 2 entries, and we've got the identity matrix in the first 3 columns. First, there's no possibility for columns 1 or 2 to change, so it's 1, 0, 0, 0, 1, 0. Next, we're not going to change row 3, so let's put in the 1, 1. Should be our last step, so we should remind ourselves it was augmented by reproducing that symbol. Now we can start. Take -2 times row 3, add it to row 2, and we'll get 0, -2. Next operation, just -1 times row 3, added to row 1 is going to produce 0, 0. Now the coefficients are relative to x1, x2, x3. So we can just say that this implies x1 is 0, x2 is -2, and x3 is a +1. And in a certain sense, we're done. But once again, if you stopped right here, it's kind of a disservice because we need to recognize that symbol, its meaning and what it implies when it comes up. So the best way to get through this section is definitely, I encourage you to write out to this step. The real conclusion we want to make is, therefore, the coordinate vector of P, we're referring to now this original function, relative to the basis B it asked, so we're talking about that basis, the non-standard one, is those 3 values we just produced, 0, -2, 1. So even though we worked all of this inside R3, my claim is that's the right stuff. But any questions at all, folks, so far? Okay, well, we got through the coordinate mapping section, and it is a kind of a tricky section to be completely upfront with you. But when you're working these kinds of problems, always just remind yourself it's about the coefficients. And even though this is a longer problem, there is a fast check on this thing. If we really have the right thing, then we should be able to take this basis, this polynomial, if I could maybe just screenshot it, maybe that might be faster. Then we should take these coordinates right here and show that we really get that polynomial. So the conclusion is up there. Let's call this the check. So let's take next, with those values right here, P of t would be equal to 0 times P1 minus 2 times P2 plus 1 times P3, where once again, this is P1, P2, P3. So let's actually do the algebra right here and see what it comes out as. This will be negative 2 times P2, so T plus T squared, plus 1 times P3, so just that function, 1 plus 2T plus T squared. Let's distribute the negative 2 to start. Over here, we get negative 2T minus 2T squared, then plus 1 plus 2T plus T squared. And provided no mistakes were made whatsoever, we should get to this function. So let's double check here. We have negative 2T, positive 2T, so that's definitely on the right track. We have a constant 1, so that helps out. Then negative 2T squared plus T squared is the negative T squared. And so I'll put a check here just to say the check succeeded. We really do produce that real function, P of T, when we use those coordinates, forming this linear combination. Well, we did it, folks. Linear algebra is definitely a weird science, I'd say, but if you get the feel for working in R3, you know a great deal of linear algebra. You just sometimes have to deal with strange terminologies like these and isomorphisms and all that fun stuff. Any questions or comments at the moment so far, folks? Okay, well, we've got about 13 minutes and some change, so let's take a look at the next section. Let's save this up. I definitely don't want to go too far into the next section, but there's a nice natural stopping point that we're going to try to get to. So we're now finally in section 4.5, the dimension of a vector space. Takes a lot of work to get here. A lot of it work is terminology, and a lot of it is just playing in Rn so we can get a really good feel for what vector spaces look like and how they act. Now, after all of that work, here is section 4.5. It doesn't start off by defining what the dimension of a vector space is, because like we were hinting at the start of class, there is some tricky work that we have to do. This is not a proof-based course, so I don't have any of the proofs to these theorems, but I think you would agree that a lot of these seem really, really plausible, and that we used similar ideas in the past. It says here on theorem 9, if a vector space V has a basis, say B1 through Bn, containing n vectors, then the theorem 9 claim says any set in V containing more than n vectors must be linearly dependent. And that's a fact we use repeatedly. Let's put down a quick example. The set of vectors, let's make it be 1, 1, 1, 3, 0, 5, is linearly dependent. And I thought I had enough space, but I don't think I do any longer. Let's add just a little bit more. That is linearly dependent in R2 because I think a lot of people would say there are more vectors than there are entries per vector. And that's the right thought to make. Or you could put all these into a matrix A, solve a homogeneous equation, AX equals 0. And a lot of people might be thinking there's automatically one free variable in this guaranteed. That's linear dependence. But I want to do it through theorem 9. That's a nice new way to analyze this problem. Those three vectors are automatically linearly dependent because R2 has a basis with two vectors. Well, it has infinitely many different bases with two vectors, but let's name this one. Namely, E, we're giving the standard basis, which is E1, E2. Like we wrote in the notes before, E1 is 1, 0, E2 is 0, 1, just the columns of the 2x2 identity matrix. But that's a basis with two vectors. And the theorem says any set in V rather, containing more than two vectors in R2 Here's that set. It's automatically linearly dependent. So that's a really fast argument. And one thing that's kind of noteworthy about this is a lot of our arguments are now just purely words. You don't necessarily have to do any mathematics, row reductions, or determinants. Sometimes you're just tying together statements from theorems like you see here. Well, any questions at all, folks, about theorem number 9? Okay, well, theorem 9 definitely seems plausible based on our work in chapter 1, but it's an amazing theorem once you're looking at stuff relative to vector spaces like these, functional spaces. So for this example 1, it says give a basis for P2, so you can name anything that's a true basis. But if you want to do the minimum amount of work, I encourage you to go this route. The standard basis, E, is going to be equal to 1 t and t squared. And because it's going to be relevant in the next part, part B, let's mention this basis has 3 vectors. Next, we go down to this problem right here. This one's tricky because of typesetting. I'll usually put extra white space here if counting the number of vectors is critical. So watch out for the commas, that should help us out. And let's see, I would probably even space this one out a little bit more as well, just so that it's easily able to tell how many vectors are in there. So we have a set B, and we want to explain why B is linearly dependent. That's almost confusing in a way. Just because we write the cursive B, or sometimes called script B, does not mean it's necessarily a basis. So this one's automatically linearly dependent. Any volunteers for the quick explanation of why? I would say probably the best. Oh, sorry, go ahead.
I don't know.
Oh, no worries. It's definitely a tricky problem, but what I would do is first count the number of vectors in that basis right here. It would be my very first step right here. Let's say B is linearly dependent because it is a set with, and again, that's why the commas and spacing is really critical. We have 1, 2, 3, 4 different vectors. One of them is a constant polynomial. So it's a set with 4 vectors. But now this says if a vector space V has a basis containing n vectors, say 3 of them, then any set in V, say this one, containing more than 3 vectors, automatically linearly dependent. So we come down here, and we get to say it's linearly dependent because it's a set with 4 vectors, and a basis for B has only 3 vectors. So it's this part right here. The fact that we found 4 vectors inside the set, which is what gave automatic linear dependence. And this is the analogy above. In R2, our standard basis has 2 vectors. So any set containing more than 2 vectors, automatically it's linearly dependent. Just really weird to see it from this point of view when it's not vectors in R2. Well, any questions at all, folks, with this problem here? Okay, notice what this did for us. It's linearly dependent, but what we did not have to do is use a coordinate mapping to make a vector in R3 out of all 4 of these different ones, put it into a big matrix and row reduce, trying to find the number of pivot columns. So if we use theorem 9, then this is all a really, really fast process. And the next theorem is even more pivotal. It says that every single basis of V must consist of exactly n vectors the moment you found just one basis with n vectors. This is what's allowing us to build a function. If every basis has exactly n vectors, then that number n is intrinsic to the vector space. We'll call it the dimension, and that's what we're going to get into down here. If a set V is spanned by a finite set, we'll call it finite dimensional, and the dimension of that vector space V is just the number of vectors in any basis for V. We definitely have a lot to say. You can tell with these blanked out examples we'll be providing, but this is what we'll be working on Thursday's class. The way we make it work is through that definition. We'll review when we come back on Thursday, starting on our example 2. Well, any last questions, folks, before we call it a night? Okay, well, I think this is a good stopping point for us. When we come back on Thursday's class, we should be able to finish out these notes, but I'll post the next section notes as well, just in case we finish it really quick for some weird reason. I'm going to try to get ahead and posting one additional set. But this is all I have for folks today. I don't want to try to rush through this one. This is an important example as well. So we'll see you all next class, where we'll be right back here.
Thank you.
Thanks so much.
Have a good one.